Can you hear me? Hello? Hello?
Hello, sir. We are hearing you, sir.
Yeah.
Good evening, sir.
Yeah. Mr. Shoyinka Oladipupo. It seems
Good evening, sir.
It seems this is your first time joining us, right?
This is the second time, sir.
When was the first time?
I think it was 2 weeks ago. I missed the class for some time.
But last week we had to shift it to 8 p.m.
Yes, I got the message late. The mail didn't deliver on my phone on time. So when I got the message, in fact, it was the second day that I got the message.
Probably your network was down or something.
I thought as much, sir.
So, yeah, sixth topic now. So that's what I'm going to display right now. So let's go through it. Can you see the screen now?
Yes, sir.
Good. The last time, that was last week Thursday, we had our class and we talked about we talked about entropy and the second law of thermodynamics. Can you see that on the screen? What can you see on the screen?
Still the same topic, sir. Thermodynamic potentials.
Okay. Last week okay, let me stop this share and let me just go through what we had last week. So entropy and the second law of thermodynamics, and we're able to touch a number of points in which we talk about a reversible and irreversible process. We said that entropy can be defined as the degree of disorderliness of a system. And we also made it quite clear that entropy of a system does not always obey a conservation law. So we now say that the change in entropy of a system that takes place from the initial state to the final state depends on the quantity of heat transferred and the temperature. So entropy is simply defined as the rate of change of energy with temperature. That is why the unit is joules per Kelvin. Can you say that? Joules per Kelvin. So it is from the initial. So this S final minus S initial is talking about a system where we have probably okay, which will be described in the next slide. We said that for a reversible process that occurs in a closed system, the entropy always remains constant. So for a reversible process, entropy is always constant, is always 0. So I was mentioned the irreversible process where we talk about a heat sink where we have two reservoirs, the hot reservoir and the cold reservoir, in which it moves from the hot reservoir to the cold reservoir until they attain equilibrium. So basically, that gives you an idea of what we're talking about. So if it is lost by the system concerned, Q will be negative, but if it is gained, Q will be what? Positive, then divided by the temperature. Hello, can you hear me?
Yes, sir. We can hear you, sir.
I seem to be having some issues with this. Let me stop this here. Okay. Let me proceed. So I will talk about an irreversible process. That's what we just talked about. So the next slide is talking about the so you note this. Okay, let me go back to that slide. You note that the entropy for a reversible process is 0. Then we'll still make a generalized statement very soon. For an irreversible process, that's what we're describing. So to the next slide, this is the two reservoirs, the hot reservoir and the cold reservoir. So if it is moving, if it is being lost by system 1 to system 2, we say that the Q here will be negative. So we say the change in entropy of the cold reservoir will be, in the cold reservoir, this C denote the cold, will be Q over TC. And that is positive because it's gaining energy. It's gaining energy in form of heat. And for the hot reservoir is losing heat, it will be negative. So by the time you bring the two together, it will be the air should be DSH plus change in SC. So the negative would have cancelled out. So now, which shows that minus Q of TH plus Q of TC is greater than 0. Now, there's a generalized statement we will make now that says that the total entropy is greater than 0 because TH is greater than TC. We can say that change in entropy is also greater than 0. So now, going to the generalized statement I said, comments coming up. Okay. We now say that reversible adiabatic process is this. Okay. We now say that for a reversible adiabatic process, during an adiabatic process, change in the quantity of energy is 0. We said that before. This implies that during reversible adiabatic process, change in the quantity of energy is 0. So the S is also 0. But for reversible, we said that it is also it gives us our former expression, which is Q over T. And we make the generalized statement that entropy can either be greater than or equal to 0. Let me go to that. Entropy is always greater than, let me go to that slide, which is of importance. Okay, this is it. The statement of the second law. We say that if a process occurs in a closed system, the entropy of the system increases for irreversible process and remains constant for a reversible process. So that means entropy of a system can never decrease. It's either 0 or greater than 0. Please note that. Now, I want to also quickly look at the Carnot engine. The Carnot engine is the most efficient kind of heat engine, and because of this, it is sometimes referred to as an ideal engine. Ideal in the sense that all processes in the cycle are reversible and no wasteful energy transfer occurs due to friction and turbulence. The engine was named after that scientist, that Sadi Carnot. So the PV diagram that I will show next will show you different stages of Carnot or different stages of the cycle. Let's quickly look at that. We're looking at two slides together. Are you still there?
Yes, sir. We are still here, sir.
Good. Now let's look at this process. Now look at the Carnot cycle. Can see we have stage DE, which is described by QH, DE, EF, FG, and GD. Now, going through describing each process one after the other. Now we look at stage DE. Now, looking at stage DE there, we said that during the process DE is an isothermal process. Please, you can screenshot this, it will help you. You can screenshot this and the PV diagram for Carnot cycle. Can you quickly do that? If you have done that, let me know. You can do a screenshot. If you're using your phone, do a
Done.
screenshot. This is
Done,
just
sir.
done, okay? You've done this. Oh, so I should take it to the other one.
Yes, sir.
Good. Because the two describe the process of a Carnot engine. So if you do this too, let me know when you are done.
I'm done.
What about the Amin? Are you still there?
Yes, sir. Done.
Okay. So having said that, you now said that process DE. So you can look at the process DE in your own screenshots now, the diagram itself. You know, that the process D is an isothermal process during which its QH is transferred at temperature TH to the working from the hot reservoir. This causes the gas to undergo isothermal expansion. Can you see that? Isothermal expansion. The next stage to it is process EF, just by the right-hand side, is going clockwise. Process EF is an adiabatic expansion. So no heat is added at the working substance as the working substance expands from volume VE to VF. So temperature decreases during the process from TH to TC. Can you see? Can you see there is a temperature decrease here? Is that clear? Is that clear? Hello?
Okay, sir.
Good. So process FG is an isothermal process during which its QC is transferred at temperature TC from the working to cold reservoir. This gas undergo isothermal compression. If you note the trend, the first two is expansion, isothermal and adiabatic expansion. So the process FG is an isothermal process in which QC is transferred at temperature TC from the working to the cold reservoir, just the opposite of process DE. And the gas undergo isothermal compression from VF to VE. You know, we said for DE, we said that goes isothermal, what's it called? Expansion from VD to VE, but this one is compression from VF to VG. Then lastly, process GD is an adiabatic compression that no heat is transferred at the working, as the working process compresses substance compressed from volume VG to VD. Temperature increases during the process from TC to TH. I think that is that about that. So let's quickly look at, I think we defined the last stage. I'm just trying to do this for those that didn't attend the class last week. So I said from the first law of thermodynamics, change in internal energy will be equals to the heat minus the work done. So the total work done during a cycle process can be calculated. So that is what we calculated there. So I said they should read up efficiency of Carnot engines last week. So if you have not done that, you have a lot of work to do. So let me quickly share the material for today. Thermodynamic potentials. So I said at the end of intended learning outcomes, by the end of this unit, you should be able to name all the thermodynamic potentials, define each of the thermodynamic potentials, derive differential forms of the thermodynamic potentials, and mention the process that each of the thermodynamics of these thermodynamic potentials. So we will say the four thermodynamic potentials are what? Internal energy, enthalpy, Helmholtz free energy, then Gibbs free energy. So can you say the four thermodynamic potentials now? So depending on the thermodynamic construction of the system, there's always convenience to use a particular thermodynamic potential to describe a system. For example, Helmholtz free energy A can be used to describe a system which is in which temperature and volume are held constant. The equilibrium condition for this system is D of A equals to 0. Change in A, that means change in the Helmholtz free energy is equals to 0. Gibbs free energy can be used to describe equilibrium between phases, since the two phases are share the same pressure and temperature. So from that, differential form of the thermodynamic potential. So the first one here, du equals to dq plus dw1 minus p dv. I think we have actually explained this in one of our classes before, but this one is talking about the internal energy, the differential form of the thermodynamic potential. So if you are told to put the differential form of the internal energy, I think this one is the Helmholtz. The H here is what? Let me go back to that. The H here is the enthalpy is the H. Then Helmholtz is A. Can you see? Helmholtz is A, and Gibbs free energy is this. Now, this is their differential form, but the one that you are always used to, that you will see every time, is T temperature multiplied by change in entropy minus pressure multiplied by change in volume. Then for the enthalpy, it is temperature multiplied by change in entropy plus volume and multiplied by change in pressure. Then for the Helmholtz free energy, it is entropy multiplied by change in temperature minus pressure multiplied by change in volume. So you note all this because we are going to the course material itself and we'll see some examples. These are just excerpts from the note. So equations above are for conditions under which only reversible work done on or by a system. We've explained that work can be done by the system or on the system. It's as if you can beat someone and you can be beaten. Do you understand? So work done on a system, that means probably someone is beating you up or slapping you, or by a system, if you are slapping somebody. I think that's a very funny example. So work can be done on a system, provided you are the system. Work can be done on or by the system. And PDV of work expansion or compression. So we're talking about expansion or compression as the case may be. That's why we change in volume, change in pressure, and the case like that. So depending on the constraints imposed on a system, it is always convenient to use a particular thermodynamic potential to describe a system. So in this live session now, we will try to describe the 4 Maxwell's relation, and these relations are useful in thermodynamic calculation. For example, one can replace a derivative of entropy with a derivative of a simple thermodynamic relation such as temperature. So let's go to the course material itself. Let me unshare this. Let me share this. Are you still there?
Yes, sir.
Yes, sir.
Good. Now let me go to the course material itself, because the course material is your guide for this course. I don't think, except you just want to. Who is taking PHY203 among you? Who is taking PHY203? I mean, I think you're taking PHY203.
No, sir.
Okay, what about Mr. Are you taking PHY203?
No, sir.
Okay. Because there was a particular question we deliberated on our WhatsApp page yesterday, and we were able to achieve a lot. So is it that you've done it before, you are yet to do it, you are yet to register for it? Did you get my question?
I don't get it right, sir.
I said, is it that you have done PHY273 or you have not registered for it? Have you done PHY207?
Personally, I've not gotten through the something very well. So I don't know if I'm still going to do it or maybe it's part of the courses that I've skipped because I entered through direct entry.
Okay.
So I don't know if it is part of something that I have skipped.
Okay.
I don't think that I will do it because science education. I just borrow physics
Okay.
this month.
Okay.
So
I didn't do that.
just like me as well.
Okay.
I'm doing integrated science education, so it's a borrowed course somehow.
Okay. So I think I told them last week that they should read up its engines. So because the previous topic was what I summarized for you before the last one. That is the Carnot engine. You know, I said you should read up efficiency of a Carnot engine. So by the time you read the efficiency of the Carnot engine, you should be able to calculate what's it called? You should be able to solve these questions. I think the 3 questions and the efficiency of a Carnot engine should not be a problem to you. So I told them to read up its engines. So the basic operation of a heat engine. By the time you read that up, you should not have any problem. I think I've described the what? The Carnot cycle to you. So I think I've even touched a good part of it. By the time you read it all up, you should be able to at least achieve something. So I said, I think I mentioned refrigerator for them, it's engines and refrigerator, because this is just page 96 of the material. It's just related to what the Carnot engine I've explained earlier. So by the time you read it, it will be, what's it called? It will be easy for you reading it because it is related to the Carnot cycle. Then that was why this is module 3. Module 3 started with combined first and second laws. I think I skipped that. Then I went straight to thermodynamic potential. So you have to read up this as well, which is straightforward as well. It's just related to what we've been doing since. I'm just picking topics so that we can cover a good number of topics. Those ones are calculations, and I cannot bring calculations to the slide. Something you read, then you have issues with it, you come to the group. So I've explained thermodynamic potentials. You can see we've talked about all this. And if you read it up, I think I've whet your appetite enough. You can always access this video on YouTube or on the course platform. So if you have any issues with it, so I've described all of them. So just derive each of the 4 thermodynamic potential is there. Derive the derivation from the 4 thermodynamic potential. So I've treated that one as well. I guess the next topic to look at is the Maxwell relation of thermodynamics. So I think that is what we will treat next week. Next week will be the Maxwell relation of thermodynamics. And the last class will be, let me see, Maxwell, then the last one will be phase transition. But I might take the Maxwell and phase transition together in our next class. Then on the last day, that's if we are going to, because next week is our 7th or 8th week, if I'm not so sure. So it is most likely that if we are, hello, can you hear me? Can you hear me? Hello?
Yes,
We
sir.
can hear you, sir.
Good.
We can hear you.
It is most likely if we are to end facilitation classes next week, it is most likely that we have 2 sessions next week, which is this module 3 and 4. Then that's between 5 and 6. Then by 8, we have the last class in which you all will be expected to come to the table with questions. So it is expected that you should read wide. As from now, I think the exam is around the corner. The timetable is already out. Practicals are ongoing for those that are taking practicals. So you should be able to read whatever we've learned before, bring it to the class next week. But if it will extend beyond next week, we won't have the second class by 8 p.m. So by the upper week, we just end the class. But before then too, you should read up. You should read up, and before you know it, we are good to go. So is there any question for what we have checked so far? Yes. Is there any question?
I don't really have questions, sir, but it's just that me personally, I'm just struggling to catch up with the course because
Yes.
I'm not a major in that aspect. So I'm just trying to pull myself together so that I can
So
catch up.
you can still catch up, because what you just need to do is, what I always advise students to do is that what are you on the WhatsApp group?
No, sir. You said we should send our number on the mail. I sent my number, but I've not been added.
Okay, let me drop my number for you. Then you can just chat me. I will tell them to add you up on the group.
Okay, sir.
But those that drop their number, they've been added.
I have not been added, sir.
So from there, you can interact with your colleagues. I think I've dropped my number for you. I've answered your questions. So what you just need to do,
Okay, sir.
the course material is not too voluminous, 164 pages. Just read it and jot. That's the first step. By the time you read and jot, you would have reduced the 164 pages to about 80 pages. Then from the 80 pages, you now take it topic by topic. Before you know it, you have covered it. Because there are some things that are not relevant, and you would have weeded off, or you would have jotted the salient points, you would have sieved them. So before you know it, you'll be good to go. Is that clear?
Okay, sir.
So I mean, do you have any questions? So I will expect that before this time next week, you read up the material. It's quite interesting. You can still go to the platform. You type PHY207 on your YouTube, you see all these videos, topic 1 to 6. Even this one now, immediately we are done, is going to YouTube, so you can watch again. So any topic you don't understand, then you can always bring your questions to the WhatsApp. We will definitely be added today. I'll be expecting that you send me a message, an SMS, sending your number. You just please add. So I'll copy, I'll just place there. They will add you immediately. Is that clear?
Okay, sir.
So,
okay, sir.
So it's expected that you read up and by let's say Monday, Tuesday, as you start seeing your questions, any gray area you don't understand, you should be able to come up with questions, so that you can even throw it open. Students will deliberate on it. People will give you instances, and with that, you will not forget. So by the time have you gone for your TMA?
Yes, I've not done the first one. No.
So you should.
I'm not sure.
You should try and do
I'm
it.
not sure with that.
Read up the first 3 or so classes. I think that should be enough to take you through this thing. So,
okay, sir.
So I think it's on this note we end this class. Thank you for coming. So note that next week, if we are to end the what's it called, the facilitation session next week, we have 2 classes, 7 and 8. But if we are not ending it next week, we have a class 5 to 6, then 8 to 9. But if we are not having it next week, Then we'll do a class, a normal class 5 to 6. Then later on, upper week, we do our final class. So
All right, sir.
thank you
Thank you, sir.
for joining the class. All right, take care, bye-bye.
Bye.